Welcome. In this third lecture of week 3, we shall be paying closer attention to cluster sample design. This lecture covers cluster sampling, a method used when a complete population list is unavailable or the population is geographically dispersed. It involves randomly selecting pre-existing groups, and these are the clusters, like households or schools. And after selecting them randomly, sampling all individuals within the chosen clusters. Logistically, it's simpler and it's more economical than simple random sampling. However, it introduces a design effect due to the intracluster correlation. That is, the tendency of individuals within a cluster to be similar. This correlation among individuals belonging to the same cluster reduces the precision of our estimates, thus requiring a larger sample size and also specialized analysis to maintain statistical power and to ensure that the results are representative of the larger population. Recall our lecture on random sampling. In random sampling, each member of the population has an equal chance of selection, and thus an unbiased chance of belonging to the sample. A random sample represents the target population, which constitutes the sampling frame. In order to do random sampling properly, you would require a list of all population members. There are circumstances when random sampling is not feasible, when the population as a whole cannot be enumerated, when the population covers a wide geographic area. So for example, if we're looking at the whole country, there are also circumstances under which the potential for contamination of interventions after randomization can occur. And so in such cases, we may not be able to randomly sample. Studies of healthcare practices or educational or community interventions can also not use random sampling. So what is the definition? In the selection process, the sampling units consist of one or more mutually exclusive groups. And this is the key distinction with random sampling, wherein it is the individuals or units of observation that constitute the sampling units. So in cluster sampling, the units of observation are mutually exclusive groups. And these groups arise through natural grouping within the population. So these are not unnatural groups. In cluster sampling, each cluster has an equal chance of being selected from the list of all clusters. Examples of clusters. So clusters could be spatial, could be organizational, or could be temporal. And so when we look at spatial clusters, we're looking at things like words, households, and for organizational clusters, it could be schools or physician practices or clinics or hospitals, as the case may be. Clusters based on time could relate to day of the week. From all this, we see that these are some sort of naturally occurring groupings. Compared with simple random sampling, there's a greater likelihood that the sample would not be representative of the population. And we've already emphasized and mentioned that cluster sampling requires larger sample sizes than for simple random samples. The clustering requires that we make adjustments in analysis. In contrast to these disadvantages, there are certain advantages to be gained from cluster sampling. Only members of selected clusters need to be enumerated and studied. Members of the sample are physically together in groups rather than scattered all over the study population. It is more economical compared to the other method, and it is easier to obtain a large sample size using this approach. In multi-stage sampling, there is stratification at the first stage, for example the geopolitical zone, and then each subgroup or stratum of the population is represented and can be analyzed separately. Stratification helps to increase the precision of estimates and to increase the power of the study by reducing variance. It is very important to distinguish between stratification at the point of sampling from stratification in analysis. So, stratification in multi-stage sampling occurs before we collect the data, while stratification in analysis occurs after we have collected the data. We have what is known as the primary sampling unit, and this is the first stage of random selection. So, for example, states within a geopolitical zone. We can study all members of a selected cluster or randomly select clusters within a cluster. So within the state, we can have clusters of local governments, and within local government, we can have clusters of wards. Only in the final selected clusters are individual units listed and sampled. Let us look at the DHS methodology. So the DHS conducts periodic nationwide surveys looking at various health outcomes. And so in the DHS method, the census enumeration area from the population and housing census constitutes the sampling frame for the survey. And these enumeration areas are the primary sampling units. So they are the clusters for the survey. And so as an example, in the 2010 malaria indicator survey, the sample was selected using a two-stage stratified design. During the first stage, the survey selected 240 clusters, 83 of them in the urban areas and 157 in the rural areas. And so you note that this constitutes the strata used, urban versus rural areas. A list of all the households in the selected enumeration areas constituted the sampling frame for selecting households in the second stage. So, in the second stage, households were selected using equal probability systematic sampling. And finally, all women aged 15 to 49 years of age in the selected households were eligible for individual interviews. And here's a graphic illustration of all that we just described. So the primary sampling unit consisted of urban and rural strata, and 240 of these were selected by random sampling. And then within each of these primary sampling unit, that is the enumeration areas, the list of households were obtained, and this was the sampling frame. And a number of households were then selected using random systematic sampling. And within each of the selected households, all eligible women were now interviewed. And so this is an example of multi-stage sampling that uses various clusters. So the first cluster was the primary sampling unit, which is the enumeration area, and the second cluster consists of households. And then within the selected cluster, all eligible individuals were interviewed. But here's the problem. Clusters typically differ in size. And because they differ in size, we could have unequal selection probabilities. And so there is a need to adjust so that the sample will be representative of the population. There are two methods that are used to adjust for unequal selection probabilities. The first one is proportional sampling, and the second is weighted analysis. Consider this table showing 6 communities with differing populations, ranging from as low as 200 to as high as 1,200. So each of these communities, which represents a cluster, has different population sizes. And so it becomes immediately apparent that if we're to select individuals from these using the cluster sampling approach, we're going to have unequal probabilities of selection. So the method of proportional sampling proceeds as follows. The total population is now divided by the number of clusters to be sampled. So if, for example, we are going to sample 3 clusters and the total population is 4,100, as we see on this table, the cumulative population here is 4,100. We divide by the 3 clusters, the number of clusters we're going to survey, 3. And so that gives us a figure of 1,367. And so the next step is to generate a random number from 1 to 1,367. And so, for example, our random number generated is 241. And so when we look at community 1 that has a population of 1,000, we see that the 241st individual is going to fall within the first community, because the community has a population of 1,000. And so we add our sampling interval, which happens to be 1,367. And so we have 241 plus 1,367, which takes us to 1,608. And 1,608 gives us 1,608 plus the sampling interval gives us 2,975. So that means that we're going to select subsequently communities 4 and 5. So the 3 clusters we're going to select will be community 1, community 4, and community 5. How is that so? Remember, the first number we selected at random is 241. So the 241st individual belongs to community 1. The second starting point for us will be 1,608. And so if we look here at the cumulative population, we find that the 1,608th individual is going to be in community 4. The next interval is 2,975, and if you look here, that individual falls within the 5th community. And so thus we're selecting community 1, 4, and 5. What are the advantages of this approach? It leads to communities being selected with probability proportional to their size. It is self-weighting, so a weighted analysis is not required. The alternative method of selecting the number of members of the cluster proportional to the size of the cluster gives a more biased estimate of true population value. In a special case, it's possible for the same cluster to be chosen twice if the population is greater than the sampling interval. It's more likely if the number of communities selected is large. The proper approach is to select 2 subsamples of the chosen cluster. It is inappropriate to select another community or to repeat the entire sampling procedure until no clusters are repeated. So, in a case where the same cluster might be chosen more than once, then the proper approach is to select 2 subsamples of the chosen cluster. When we do cluster sampling, there are certain considerations that need to be considered, or that need to be at the fore. We need to understand that members of a cluster tend to be more alike than members of the population as a whole. So if, for example, I selected a village in Kogi State, of course, it stands to reason that the members of that village are going to be more alike compared to, let's say, members of another cluster that we selected in, let's say, Kano State. Members from the same cluster tend to provide less information about the population as a whole than do members from different clusters. This reduction in information translates into estimates that are likely to be less precise than estimates obtained using simple random sampling. Cluster sampling increases the variance and widens the confidence intervals of our population estimates. So in other words, cluster sampling reduces study power. And so to offset that, requires us to have a larger sample size than we would require for simple random sampling. Increasing the number of clusters is better than increasing the number of members sampled in each cluster. And thus we come to intracluster correlation. The intracluster correlation coefficient defines how related members of a cluster are. These coefficients are typically small. A high intracluster correlation coefficient, that is, if it's close to 1, means units within clusters are very similar, while a low value, being closer to 0, means units within clusters are independent. A synonym for the intracluster correlation is the rate of homogeneity. And what does it measure? The intracluster correlation measures the variability between clusters compared with variability within clusters. This information is essential for us to be able to calculate the design effect. Minimal intracluster correlation of demographic variables gives us a rho that is close to 0. And so typically age, sex, marital status tend to have lower intracluster correlation. In other words, they tend to be more independently distributed. On the other hand, the intracluster correlation is greater, often ranging between 0.1 to 0.3 in regard to health practices and socioeconomic variables, such as income level, educational status, and so on. A point to be noted is that the intracluster correlation can also be affected by the variability of interviewers, because different clusters will be interviewed by different interviewers, and each interviewer may have their own peculiar idiosyncrasies which affect how they collect data, and this itself can impose some form of intracluster correlation. And so the intracluster correlation is basically the variance between the clusters divided by the sum of the variance within and the variance between. In other words, the between variance divided by the total variance. And when you think about this evokes some of the concepts we had seen in an earlier lecture related to analysis of variance. So these are related concepts. So, sample size calculation in cluster sample. The design effect is the ratio of the number of subjects we require using cluster sample versus the random sample. So for cluster sampling with m members per cluster and an intracluster correlation coefficient rho for the variable under study, the design effect is given to us by the formula we see: 1 plus m minus 1, all multiplied by rho. It is better to have many clusters with fewer subjects per cluster than few clusters with many subjects. The number in each cluster is best chosen on practical grounds. For example, the number of units that can be surveyed in one day. The intracluster correlation coefficient can be estimated based on the type of variable studied. Recall we already said age, sex, marital status, for example, have minimal intracluster correlation, whereas health practices, socioeconomic variables tend to have a larger role, ranging between 0.1 to 0.3. The number of clusters that we're going to select can be given to us by this formula. So P is the estimated proportion with the condition, D is the design effect, E is the sampling error, M is the number of subjects in each cluster. So from this we see that if we reduce M, the number of clusters will increase. And if we increase m, the number of clusters will reduce. Recall in an earlier slide, we already mentioned that it is far better to have more clusters than to increase the number of subjects per cluster. I provide this link for those interested in further reading up on this concept.